Hello everyone, my name is Diego. I am a postdoctoral researcher at the Singapore MIT Alliance for Research and Technology. CoAIcoder is a project I developed when I was a PhD student at the Singapore University of Technology and Design, in collaboration with my colleagues from the Fudan University. In many disciplines like psychology, social science, and human-computer interaction, researchers need to analyze qualitative data to extract valuable insights. Grounding theory and semantic analysis are the two key methods employed for this purpose. Sadhana, in his coding manual book for qualitative researchers, simplifies them into a code-to-theory model. Specifically, the processing involves transforming unstructured data into a series of categories, themes, and ultimately concepts after quantitative coding. However, this process is often manual, time-consuming, and labor-intensive, especially in collaborative setting. Collaborative qualitative analysis is crucial for building a stronger interpretation of the data, but it is also significantly more time-consuming and labor-intensive. As AI's ability to understand and process text data rapidly grows, we're firstly starting to think the following questions in this research. Can we utilize AI in collaborative qualitative analysis? Does it truly work? Can this improve the efficiency of CQA? With our motivation, we examined existing research in this field and discovered that AI has primarily been applied to individual qualitative analysis, while collaborative qualitative analysis relies solely on traditional software. Specifically, in individual analysis, researchers have leveraged various methods, including keyword-based code rules for pattern matching in textual data, and topic modeling and text classification for large-scale data. Conversely, research on CQA still employed traditional methods, such as manually labeling and ordering disagreements between coders to direct their efforts towards crucial sections of the text data. On the commercial software side, Envivo, XQDA, and Atlas TI offer the limited support for CQA, and these tools also require significant manual effort. Consequently, there is a research gap regarding how AI can be effectively integrated into CQA workflows. To gain a deeper understanding of how AI can be used in CQA, we conducted semi-structured interviews with 8 qualitative researchers who have at least 1.5 years qualitative experience. This included 2 postdoctoral researchers, 3 PhD students, and 3 master's students. They came from various research domains, such as HCI, healthcare, AI, VR, and Ubicom. They had experience using various qualitative data analysis software, including Excel, Atlas TI, MaxQDA, and Envivo. During the interview, we asked their CQA practices, the difficulties they faced during collaboration, and their expectations for the role of AI in CQA. Each interview lasted 20 to 40 minutes. After the interview, we conducted a thematic analysis of the interview transcripts to identify key findings in the 3 aspects. Our results found that while they generally follow the 6-step process described by Richard et al., however, the level of strictness and the specific methods employed varied. Interestingly, thematic analysis appeared to offer greater flexibility than grounded theory in terms of coding independence and the number of coding steps, etc., and therefore it needs less resources. For example, P4 said, I think the reason for following a strict CQA process may be because we have more people and collaborators, and the paper depends on the qualities of the codes we have evolved. The results also highlighted several difficulties. Specifically, coders emphasized the significant time investment. They raised concerns regarding the possibility being influenced by each other's interpretations. They mentioned a lack of robust collaborative features in current qualitative data analysis software. For example, P5 said, I also tried to use Envivo to do collaboration. I found that when using Envivo, I cannot group together codes and text from 3 coders automatically, so later we just used Excel. They also mentioned that the predefined codebooks could restrict the development of new codes. Lastly, they mentioned the inherent subjectivity of the qualitative data analysis, which could lead to different interpretations from different coders. They also found 2 suggestions or expectations from users. They expected that AI can help to match the code suggestions in code history and to detect coding conflicts in real time, decrease the iterations. For example, P1 said, so if this content and that content suddenly matches up, it would be nice for AI to just assist me and say, hey, you have done this before, why don't you assign similar code to this data? For more specific qualitative results, please refer to our paper. Our findings lead to the following 6 key design considerations for AI-assisted CQA. The system should enable coders to maintain independence during the initial open coding stage, while also providing user-friendly features for coding convenience. The system should use a familiar interface similar to existing user-friendly software like Google Docs, which can minimize the learning curve for coders. The system should also offer collaborative settings such as AI-mediated collaboration. Similar to previous research, the system should also provide a list of code suggestions tailored to specific content being analyzed. However, it should also allow users to choose whether or not to request and utilize these suggestions, promoting user autonomy. Lastly, the system should be designed to support inductive coding during the analysis phase, as opposed to solely relying on restrictive predefined codebooks that can prevent the code development. These design considerations inform the development of the CoAIcoder system, which allows researchers to conduct CQA with AI assistance. Based on the design considerations, we have developed CoAIcoder. CoAIcoder's interface is a text editor that allows users to select text first and then click on the button to request code suggestions. These suggestions are generated by a text classification model trained on users' own coding history. The numbers beside each suggestion represent the confidence score, which ranges from 0 to 1. This score is calculated based on the similarity between the code suggestion and the text. Later, when two coders collaborate, each using their own interface without seeing the others, the codes indicated in these interfaces will be collected by the backend model for training. Here in its backend part, the collected text and the code data will be formatted into a YAML file and labeled as intent and examples, respectively. The intent serves as the labels for the classification model to perform classification. It will train an NLU model using the latest data, which is updated throughout the coding process. In terms of the model setting, we have utilized a pre-trained word embedding, so the model already possesses some language understanding capabilities. Thus, users' coding data is used solely to tune the model, enabling it to suggest appropriate codes. Because we are still exploring how AI can be applied to CQA, we are not attempting to propose a definitive solution. Therefore, based on three factors, whether AI is used or not, whether coding is done synchronously or asynchronously, and whether a shared model is used or not, we have identified four feasible conditions. Condition A, without AI, asynchronously coding, not shared model. Condition B, with AI, asynchronous, not shared model. Condition C, with AI, asynchronous, shared model. Condition D, with AI, synchronous, shared model. These four conditions determine how users' coding data will be trained within the model. We then invited 64 non-expert native English speakers through public channels in Singapore's universities and trained them on the CQA process. We then grouped them into 32 pairs and divided them among the four conditions in a between subject design, with each condition comprising 8 pairs of participants. All participants were asked to collaborate with their peers to perform a CQA task on a public interview dataset, with no domain knowledge required. Each pair went through 3 main phases. Phase 1, independent open coding. Phase 2, discussing and proposing a codebook. Phase 3, applying the codebook. Lastly, we evaluated the CQA performance from 2 main aspects, coding efficiency and coding quality. Coding efficiency is measured by coding time, means how many actual minutes are used in each phase. Coding quality is measured by iterator reliability, code and subcode diversity. It means how many unique codes are generated. Code and subcode coverage means how many unique codes they generated are covered by the standard codebook. While no main effect is found for total coding time, there is a trend showing that overall coding time decreased under AI conditions. For individual coding time in each phase, we found that the coding time in phase 1 has a main effect, while no main effect for phase 2 and phase 3. However, the discussion time in phase 2 under AI conditions are lower than the baseline condition. Overall, while the significant difference is more or lacking, there is a trend that when coding with a shared model, the coding time is lower. We then measured the iterator reliability for phase 1 and phase 3. There is a main effect in phase 1. It shows a slight trend that the IR in conditions with a shared model might have been increased in phase 1, but no difference in phase 3. Phase 2 is a discussion phase, therefore we didn't calculate IRR for it. Participants also seemed to be quite satisfied when they are using shared model. At P31 side, it could have another word for introduction. For example, maybe my partner will say intro. If we want to formalize things, then we realize that introduction is a more formalized code. For code and subcode diversity, we found that conditions with the shared model tend to be lower. There is no main effect for phase 2. And for subcode diversity, there are no main effects. For code coverage metric, we did not find significant difference among 4 conditions either for phase 1 and phase 2. We have found the effect of synchronous from qualitative data. Some coders in asynchronous and shared model condition tend to rely more on the AI code suggestions. We also found the differences in coding speed could also make slower coders to rely on the code suggestions, which is actually generated based on the code history from the fast coder. For more qualitative details, please refer to our paper. To the best of knowledge, this work is the first to explore the effectiveness of such a customized model in CQA. We have identified a trade-off between coding efficiency and coding quality. AI and shared model could potentially decrease coding time and lead to a higher initial IRR, but it may also decrease coding diversity at the early stage of CQA. This suggests that while an AI and shared model can help build a shared mutual understanding among the team, it carries the risks of resulting in lower quality. Such mutual understanding could, however, facilitate stronger discussions within the team. Overall, the four conditions represent 4 different levels of independence in coding, ranging from zero dependence between coders to full dependence. We observe the various performances across the coding teams, but can we argue that the AI and shared model is the best for CQA? This depends on the application scenario. In scenarios where efficiency is more valued, a bit of reliance between coders might be beneficial. Conversely, in situations where creativity is prioritized, reducing reliance between coders might be advisable. In summary, we were the first to explore AI's application in human-to-human collaboration in qualitative analysis scenario. The takeaway for this research includes 3 aspects. Firstly, we identified the current CQA practices, difficulties, and suggestions, and developed a CoAIcoder system with 4 different collaboration conditions. We then evaluated with 64 participants and identified the trade-offs and conditions and the considerations on independence level in CQA teams. For more details, please check our paper on CoAIcoder journal website.